Hello and welcome to our series on maths education for the FET phase. This series is aimed at maths teachers in the FET phase and of course everyone else who's interested in education in our country. Time for us to take a look at our video. In today's lesson at Alexandra High School, the maths teacher Moses Poshoko is beginning a lesson about the transformation of functions.
We're going to deal with graphs and see how they behave. And then after that, you're going to be able to predict that this graph will be at this place, and that's where it will be.
The outcomes for this lesson are to explore the relationship between different transformations of algebraic formula and the corresponding transformation of the graph for the functions f of x equals mx and f of x equals ax squared. And to generalize the transformation f of x to f of x minus k.
You know the graphs are drawn on a Cartesian plane, right? How many types of graphs do you know that we have dealt with so far?
Parabola.
Hyperbola.
Straight line. Circle.
Now, we also know their shapes, am I correct? Very important.
Mr. Poshoko begins the lesson with a revision of the shape of the different graphs as well as their basic formulae.
For instance, when I've written 3x, it represents a certain graph.
A linear graph.
Remember, if I'm going to draw this on a Cartesian plane, I'll be drawing something like this. You can use...
Other graphs include the hyperbola.
Anyway, it is two parts of the shape. Above here,
the circle.
We know the distance from there to there will be what? Who knows?
And the parabola.
Will be something like this, am I right? Remember, if I can say this plus 1, I add a 1 to this graph, what is going to happen? If I say plus 1 here, what is going to happen?
In this activity, the teacher introduces a transformation of algebraic formulae and the corresponding transformation of the graph. He demonstrates using the linear graph.
This is the graph, y is equal to 3x, graph number 1, right? I say plus 1. Remember the y is what? It's 3. If I say plus 1, what's going to happen?
4.
So this point will be around here. And if x is...
The teacher substitutes different values for x and plots the new graph.
Basically, you can see that the graph, this graph, if you add a 1, what's going to happen? It moves. It is moving. And that's what we're talking about today. The movement of the graphs. I want you to work with these worksheets, fill up the information here and plot the graphs.
In this activity, learners are presented with a table and graph of y equals x squared. They are required to complete the table with 4 new graphs and then to plot these graphs onto the same graph paper.
How did you plot this point here?
Whilst the learners plot the graphs, the teacher moves between the groups and identifies learners' thinking and helps where he can.
Learners always have a problem with the scales, scaling. They have problems in terms of identifying, if you've got numbers like 5 and 10, to get a number between the two is always a problem. And the two, some of them are still struggling in terms of putting a point on a Cartesian plane. The relationship between the x and y, they actually put them at a separate position, whereas we say, what is the relationship between them? Where are they meeting? Others, they calculate wrongly, and they notice that the graph that doesn't look like a parabola anymore. They get anxious and they start saying, oh, no, this math is out of order.
Okay, so you are...
In this example of a different class, a learner is driven by previous experiences of simplifying any expression in sight. He may get the right answers, but the connection between the algebraic process of subtracting 2 and the graphing action of moving the point a length of 2 is now lost. Back at Alexandra High School, the teacher has emphasized the need to have the graphs drawn in different colors and to name each of the graphs individually. To assist in the investigation of the graphs, Mr. Poshoko has supplied learners with a piece of copper wire which is bent in the shape of the graph.
Just an estimation as well, just to estimate how. Now what I want you to do is to check using that wire of the graph to check whether graph 2, 3, 4, 5 is different from that shape. Is the shape different as you move from one graph to another?
No.
It is the same.
Yes.
Can you tell me what is the difference between the first equation as compared to the second equation? You've just said the shape is not, has not changed. What has changed? What has happened?
I've noticed that the graphs are moving.
Are they moving in the up or down? Or where are they moving?
Left and right.
Yes, of course. Very carefully look at the numbers in terms of movement to the left and to the right. When you look at this graph, which direction did it move from the original?
To the right.
And what happened to this graph?
To the right.
And this one?
Equation 4 to the left.
And this one?
Also to the left.
Now, did you notice in terms of the numbers, it depends on whether it is a plus or a minus.
Learners are starting to see that a relationship exists between the direction of movement of a graph and the adding or subtraction of a unit.
So the plus moves in which direction?
To the left if it's positive.
To the left. And for the negative numbers, the graph moves to the?
It moves to the right.
Moves to the right, okay?
From this exercise, learners see that if a value is added to the x and then all squared, the graph moves to the left, and if it is subtracted, it moves to the right. At many schools, graphing calculators are used in conjunction with an overhead projector for easy display of this movement of the graphs.
The first one that appears on the screen, the second one as they appear on that worksheet. Right? Do you see all of them?
Mr. Poshoko begins this section of the lesson with a drawing of the original graph.
Okay. The one that was negative, it moved to the? It moved to the right. Am I correct? This side. But now, how many paces did it move from here? How many units did it move?
Twice.
It moved twice.
Twice is not the correct word here, but in the context, we understand that they mean 2 units. That is, first they move it 1 unit, then another unit, so they have moved it twice.
Yeah, it moved to the, you said it moved to the right. How many paces did it move to the right?
4.
And this one, it moved to the left. How many times?
Twice.
And this one, how many times did it move?
3.
3 times. So you can actually see that the numbers here are actually even determining how far the graph is going to move either to the left or to the right. Is that not so? Right? To the right.
It is now possible for learners to predict where a graph would be from the equation.
For instance, if I say to you, equation 6, and I say y is equal to x minus 3 all squared. I want you to predict where it's going to be on the Cartesian plane. From the original, this being the original, how many paces is it going to move, and also in which direction is it going to be?
It will move to the right 3 paces.
The teacher demonstrates this movement using his copper wire.
From one place and say...
In another example, the teacher demonstrates using x plus 7 all squared.
This, you'll be able to say, am I going to move to the left or to the right? And how many paces am I going to move? 7. 1, 2, 3, 4, 5, 6, 7. And we can predict that this graph is going to even be beyond the paper that we are having. Am I correct? 3x as our original graph. And equation 2.
Mr. Poshoko writes the equations for several developments of this graph on the board.
What do you notice about these graphs? How different are they from this to that? Or do you see any similarities?
It moves to the right.
These ones were moving to the left and to the right. right? What about these ones?
Up and down.
Why do you think they won't move to the left and to the right?
When you simplify,
Learners base their argument on the fact that the 3 in front of the x is the gradient and the second unit is the y-intercept. This means that when this value is changed, the y-intercept will change, and so the graph moves up or down. The teacher reminds the learners that if the line is extended, it would be clear that the graph is also moving left or right.
Am I moving down? But notice what is happening there.
When a graphing calculator is used, this can be demonstrated clearly.
First one, the second one, the third one. Here is the fourth one.
We can conclude from this lesson that by adding a unit to the x, the graph will move to the left, and by subtracting a unit, the graph will move to the right. We can also conclude that the graph will move by the number being added or subtracted from the x value.
So this graph,
In Mr. Mdlalose's lesson on the same subject, he ends by summarizing these points on the straight line and parabola graphs. He then asks a learner to predict what would happen to a hyperbola if a value is added to the x.
of y equals to 1 over x. Okay, can somebody come over, look at what is happening in all these cases, and draw a graph of y equals to 1 over x minus 1.
It is clear that this learner does not see the hyperbola as one graph that should be shifted as a whole. The problem lies in the learner's attempt to preserve the symmetry in the figure, but this was complicated by a conception that the axes of symmetry are fixed and do not move with the graph. To summarize, learners have undoubtedly learned from the activities, but the teacher needs to now follow it up with some consolidation. Now that we've seen the video, it's time for us to welcome our guests. And today we've got Taska Matlejwane from Pafokgang Secondary School, we've got Mayra Hockman from the Wits School of Maths, and we've got Maggie Verster, who's the webmaster of the Easy Maths community website. Thank you very much for joining us. The first question to you, Mayra, why is the concept of a family of graphs important?
When we graph curves or the equations of the curves, it's important to see that the example that we choose is only one particular example in a whole class. So the students and the teachers usually graph 5 or 6 and then compare the behavior of each curve to each other. So we want to see that there's a flow, there's a pattern. Maths is about seeing patterns of behavior. So the more examples we can do which enable the pattern to become obvious to the student, the better. Once we see the pattern, then a rule can be established. So by looking at a family of curves, the students are able to predict perhaps a behavior and then to formulate some sort of rule. Essentially, after we hypothesize about the rule, we should then prove the rule, because sometimes there are exceptions. But that's the way. Do a few examples, make a prediction, make a hypothesis, try and prove your hypothesis. And then it's a rule, then we can use it.
Okay, Maggie?
Well, I think it's important to help the learners realize that all the graphs are related. If you change a number, what is it going to do the graph? If you square it, what influences is it going to have on the curve? And once they realize that they are all related, that they are a family, then they can predict what's going to happen.
Okay, Taska, you agree with that?
Yes, I quite agree with my two colleagues here. Because when you look at the graphs, they should really emphasize the fact that here we talk about systems and how these systems behave. They are not static. There's a relationship. And the set of systems or the sort of multiple graphs that which are drawn, and to observe their behavior in that way, they help the learners in that fashion to see that it's a system.
What difficulties do learners generally have with this concept, and how should teachers help them through that?
They don't see the movement happening. It's like now it's becoming a predictable thing. You say the graph was maybe sketched in a certain position. Now you draw the second graph to say it will move to that second position. But if learners don't see it happening, they missed the action, the processes, then they lose out on that. That's the first problem which I often see with them.
Okay. Mera?
Yes, in practice, from my experience with these translations, the students often get quite confused as to which direction, if it's to the left and to the right. And the natural way students like to look at is x plus something. And that something then predicts the movement. In this case, it's x minus a quantity. And that minus the quantity then predicts whether it's to the left and to the right. So it's very important for the students to understand the form there, that we're looking at x and then we're looking at x minus a. And it's the value of a after the minus sign that's telling us whether we go to the left or to the right. And this is quite a problem, and I've seen it in many students in continuing years, that students will look at x plus 3 and say, oh, we're going to the right, when they should be looking at x minus minus 3. Okay, and know that we're then going to go to the left. So it's a little bit of a technical hitch which students do have and perhaps need to be emphasized once the rule has been established.
And how should teachers help them through that?
I think through the experience, through the plotting of the curves, and the emphasis of the form, the standard form would be y equal to f of x minus k. And then we look at the value of k to predict whether it's to the left or to the right. If k is positive, it goes to the right. If k is negative, it goes to the left.
Okay, Maggie?
I can't agree with Moira more. I think we actually need to take it even a step back. One of the big problems that the learners have is plotting. When we give them these family of graphs and we ask them to plot it, I find if you go into a classroom situation, especially where there is a problem with scale, normally when we ask the learners to plot it in grade 10 and 11, we are quite adamant that the scale should be the same on the x and the y axis. Whereas in this example, there was definitely a problem with scale because they didn't correspond. So I think we must remember to help the learners, we must go back that step and just remind them about plotting basic things. We always take that for granted that they should remember that from previous grades.
We also saw the use of graphing calculators there. What do you think are the pros and cons of that?
Well, I think graphing calculators are, of course, magical things to use in a classroom. The reality, however, is that in some of our disadvantaged schools, that is not a possibility at all. So you are back in the situation where to do this lesson you have got to spend a bit of time to plot graphs, and to be able to then see the pattern that evolves takes a lot of time, whereas you can totally sidestep that by giving the learners graphic calculators and they can make whoopee and see within seconds that the transformations that happens, and that also leaves more time for them to formulate what is happening in their minds, and they're not bogged down by the actual plotting of the graphs.
Okay. Mera, pros and cons of the
Yes,
graphing
two
calculator?
things I'd like to say. I agree that it's greatly accelerating to use a calculator, to use a computer. I would again talk about the more dynamic geometry programs where one can drag the curve through all values and see a continuous movement of the curve as what we're adding or subtracting changes. However, on the other hand, the students tend to get an impression that the maths resides in the calculator. And they become disconnected from the sketching. And as Maggie has already emphasized, they need more practice to know that they can generate the curves themselves. And as much as our students now, I often have students, when you ask them to find the value of a half, they will use their calculator to work it out. Or you'll ask the student what the tan of an angle is, and he'll tell you that you just press this button of the calculator. It no longer is a ratio. It's no longer a fraction. So the students of a new generation are getting a completely different idea of the mathematics because of the technology, and we must just guard against it. I do welcome technology, and one can't not but welcome it because it's here to stay. But at the same time, one should be able to use it so that the students still retain the basic picture in their minds. It's almost a visual thing of what a half is. It's a fraction, and that the tan theta is the ratio of the opposite to the adjacent. These things shouldn't be lost with the technology.
Tasker?
The bad side of it, as he has highlighted, also is an instrument of scarcity, that many other learners may not have it, and that I think is a shortcoming.
Okay. Meira, how well do you think the teacher handled this topic?
I think that lesson was wonderful, and I loved the wire that the teacher brought in, that low-tech device in terms of using technology. That was a great device. There's a couple of issues that I would take up. The very first example was not an example of what followed. He looked at 3x plus something, which was the vertical shift, and then the lesson dealt with the horizontal shift. And the problem with the linear shift, it can always be viewed either vertically or horizontally. So the linear curve is almost an exception, and that's why it was good that he perhaps emphasized the quadratic to begin with and then moved back to the linear, where normally we would start with the linear and then progress to the quadratic. The other suggestion that I'd like to make is, once the rule was established, I would have suggested the students to draw some parabola touching anywhere on the x-axis, and to be able to predict now the equation of the curve. That is, you move the one way to get the rule, and then you use the rule to go backwards to get the equation. So there's a cycle that is completed in the lesson. Draw many curves, formulate a rule, use the rule to predict the nature of the curve. Then the students would see the power of the rule.
Okay. Maggie?
What I loved about the lesson is that it was so real. Also that the wire was wonderful. We tend to look at technology and think that it's going to save all our problems, but I thought just that simple device to me was really a wonderful instrument to make that shift that Tasker was talking about possible, that they can move it and see it keeps its shape and you move it so many places. So I actually thought that he handled the topic quite well.
Okay. Tasker?
Yes, I would agree and say the homebrew technology is always the best, very interesting for learners. And then further than that, sticking to one type of example to see it, it will limit the possibility of them getting confused about the vertical shift and the horizontal shift. That I don't think it was made very clear to learners.
Tasker, Meira and Maggie, thank you very much for your contribution. And to our viewers at home and at schools, thank you very much for joining us, and do keep your eyes peeled for Module 18 coming up soon. Goodbye.